he's going to talk about the case theory of the rational functions.
Right, thanks for the introduction and for the organizers for inviting me. Very grateful. Yeah, so I'll be talking about the K theory of a certain C-star algebra associated to a rational function.
Jeremy, could you speak up a little bit?
Oh, yeah, sorry. Yeah, so what is a rational function? It's a quotient of two polynomials defined on the complex plane. And you might be used to thinking of this as a complex valued function that's only everywhere defined, everywhere except the poles of the rational function. But we can actually extend it to a function on the Riemann sphere, which is just the extended complex plane. The way we do that is we map infinity to the limit of the values of the quotient of the polynomials. And if the denominator has a 0, then we just map that 0 to infinity.
Including if the numerator has a 0.
We're assuming that there's no common zeros of P and Q, so that won't happen.
Right. Yeah.
And actually, this is going to be a continuous map on the Riemann sphere. And moreover, if you endow the Riemann sphere with its standard structure as a Riemann surface, it'll be a holomorphic function. And you can show that all holomorphic self-maps of the Riemann sphere are rational functions. So it's a self-map, so we can consider its iterations and think of R as defining a dynamical system. And we like to study it in that way. So the most basic property of rational dynamics is that the Riemann sphere partitions into two sets. One, an open set, which is called the Fatou set, and it's where the dynamics behaves rather nicely. And then the complement, which is called the Julia set, is where the dynamics is chaotic. So the Fatou set of R is defined to be all points who have neighborhoods, such that if we restrict the iterations of R to that neighborhood, it forms a pre-compact family of mappings in the compact open topology on functions from, say, that neighborhood UZ into the Riemann sphere. One nice property about the Fatou set is that it's open and it's invariant in the sense that the preimage of the Fatou set by R is going to be the whole Fatou set. And then the complement is called the Julia set. It has some properties. So you show that repelling periodic points are densely contained in the Julia set, as well as if you take any open set in the Riemann sphere that intersects the Julia set non-trivially, I can find some number n for which the nth image of U by applying R is the whole Riemann sphere. So that open set blows up to be the whole Riemann sphere. And that's kind of interesting because so we have a lot of periodic points in the Julia set. So those orbits are really nice, but we can get as close as we want to that orbit in some open set and follow around the orbit and then eventually blow up to the whole Riemann sphere. So that's very chaotic. Here's an example of a laser. Yes. So I'm gonna just go through this a bit. See this yellow point that I denote? That's going to be a point in the, so the black pixels here are the Julia set and the white pixels are the Fatou set. The yellow point where those three red rays are intersecting is a fixed point, and it's repelling in the sense that its derivative has modulus greater than 1. So what's going on here is that this sector here is being mapped 1-to-1 on this sector here. And then this one is being mapped 1-to-1 onto this sector. And then this bit right here is being mapped 2-to-1 onto here in such a way that this point here maps to here. So you might notice some self-similarity here. So this neighborhood here looks a lot like this neighborhood here. So if this is getting mapped to here, and this looks like this, you can kind of expect this to map here, and this will map here. And you can keep playing this game, and then you see this neighborhood here looks a whole lot like here, which looks like a whole lot like here. So you can infer what the dynamics of this component is and this component, and you just keep traveling down the Julia set in this way. So you can kind of use the fractal geometry of the Julia set to understand the dynamics. And you could do something similar here. So that's something to me that's very interesting, that the geometry of the Julia set tells you a whole lot about the dynamics of the rational map. So that's another Julia set there. Here's a couple other ones with some very different structure. So this kind of tells you that the dynamics can behave in a variety of different ways. So it's a very interesting family of systems. So most of us are operator algebraists. So a natural question for us is how to define a C-star algebra from a rational function. This is done by Kajiwara and Watatani. So in this conference, we've seen the Diacono-Renaud groupoid show up a few times. I'd like just to say that that method won't work for constructing a groupoid here, because a rational function has a finite number of critical points where the map is not a local homeomorphism. So when you try and give the groupoid the same topology, what turns out happening is that the product on the groupoid is no longer continuous. So we need a different method, and the method we'll be using is to construct a transfer operator. So for a fixed point x in the Riemann sphere, we'll let the index of r at x be the multiplicity of this equation here at z equals x. So that's just a number, and another way to calculate this number is if you draw a curve around x and then compute the winding number of r around that curve. So this number is measuring how much the mapping is winding around an open neighborhood. And we'll build a transfer operator phi on C0 of x, where x is either going to be the Fatou set, the Riemann sphere, or the Julia set. And what that's doing is it's sending a function f, and it's summing over the R preimages at a point y. But we're weighting by these index terms. And if we don't weight by the index terms, we run into the same problem as constructing the groupoid. The transfer operator phi won't map continuous functions to continuous functions. So we really need to weight by these numbers. It's not too big of a deal because there's only a finite number of critical points. So this index value is only going to be greater than 1 out of a finite number of values. And so what you could do is you could construct a XL cross product in this transfer operator, and that will give you a C-star algebra. But I prefer the approach of Hilbert modules. So our Hilbert module will be this vector space E, which just turns out to be C0 of x. Its inner product will be implemented by the transfer operator, and its right C0 of x action will be implemented by precomposing with R. And there'll also be a left action by C0 of x given by pointwise multiplication functions. And so we got a correspondence E phi, and we'll denote the Kuhn-Pimsner algebra of that correspondence ORX. So some things about these algebras: the KMS states have been determined by Izumi, Kajiwara, and Watatani. These algebras fit into a short exact sequence, which kind of makes sense because the Fatou set is in sort of an invariant domain for the dynamical system. And C-star algebra associated to the rational dynamics on the Julia set is unital, simple, purely infinite, nuclear, separable, and satisfies the UCT. So in particular, it's a Kirchberg algebra. So so the Kirchberg-Phillips theorem, it's going to be classified by K0, K1, and the class of the unit in K0. So in my paper, I compute this invariant. But it's been computed already in a certain special case by Nekrashevich when the map R is hyperbolic and post-critically finite. So I won't say what that is, but turns out there's only countably many rational functions that satisfy this hypothesis. So it's not really showing the whole picture. So to understand the K theory, I need to tell you some more stuff about rational dynamics. So a Fatou component U will be a Maxwell connected open subset of Fatou set. And you can show that if U is a Fatou component, then so is its image by R. And the theorem, so this just tells you that the Fatou components are kind of they're being permuted by R. And what Sullivan shows is that eventually a Fatou component is going to be mapped into a periodic cycle of Fatou components. And such a cycle will be called a Fatou cycle. So it'll just be denoted by P, and it'll be a finite collection of Fatou components that are being cyclically permuted. And we'll denote absolute value P to be the length of that cycle. So there's a theorem that classifies the dynamics on Fatou components. I won't go into all of it, but it's due to a lot of people, Julia, Fatou, and Sullivan, for instance. So if P is a Fatou cycle, then it can either be an attracting cycle, parabolic cycle, Siegel cycle, or a Hermann cycle. And this last one is important for us because this is what actually shows up in the K3. A Hermann cycle is such that if for every component in the cycle P, if I raise R to the power of the Fatou cycle and then restrict the dynamics to U, that will be conformally conjugate to the interrational rotation on some annulus. So some pictures. We saw this one before. This right here is actually an attracting cycle of period 3. This one here is a parabolic cycle of period 3. And then so all these other balloon-shaped guys are being mapped eventually into this cycle. That's Sullivan's result. And here, this has one Siegel cycle. And all the components are eventually mapping here. And this is what we're interested in. It's the Hermann cycle. So you can see that all the cycles, if you compute their K1, they're all going to be trivial except for the Hermann cycle because it's an annulus and the rest are all simply connected. So that's why it's important. And we'd like to associate certain functions to Hermann cycles. I'd like to just go through an example here. So we'll denote curly HR to be a set of Hermann cycles. And as an example, let's say we have cycle of length 2. So we have two annuli. And these are being permuted cyclically. So what we'd like to do, and so there's some Julia set in here, Julia set in here, and out here too. What we'd like to do is orient this cycle. And since it's just an annulus, it has 2 boundary components. And for us, an orientation will just be a choice of boundary component in such a way that the orientation is compatible with the dynamics. So, for example, you could choose, maybe I should start clicking through some slides. We could choose this boundary component. See where it's mapped with by R. Say it's mapped here. And this would be an orientation for this Hermann cycle. Okay, so now the cycle is going to split the complex plane into two components. And we just like to keep track of the component that contains our chosen boundary part. So we can shade that in here. And also here. And what our functions are going to be doing is it's going to be measuring the overlapping component, how many times the components or the positively oriented components overlap. So we get a function for each Hermann cycle, which will denote HQ. And in this example, the orientation is overlapping twice in this large region. And then over here, there's only one part of the orientation. This part that's inside here. And then this part of the orientation only sees this bit here. So this function HQ would be taking values 2 on large region and then 1 on the smaller regions. That makes sense. And one thing I showed is that if I take one of these functions, apply the transfer operator to it and subtract it, that's going to be constant. And you can think of this number as sort of measuring the number of times R maps the positively connected components onto the Riemann sphere. So it's some sort of covering dimension. Okay. So we have all these functions here. And from them, I'd like to construct a matrix. So we'll denote CR, JR to be the critical points inside the Julia set. So that's just going to be the set of points C with vanishing derivative. Sorry about the messiness. And then we're going to add an extra index U. How much time do I have?
4 minutes.
Minutes, okay. So those are going to be the indexings for the rows of this matrix. And then for the columns, we're going to index by Hermann cycles. And we're going to throw in this extra index U. Basically, what the matrix is doing is it's computing the values of these functions at the critical points for entries C and Q. For entries C and U, that's going to be, we're computing just one. UQ is going to be this covering number. UU is going to be the degree of the rational map -1. So, and for 2 cycles, some more notation will denote little fr to be the number of Fatou cycles I have for a given rational map. This is always going to be a finite number. Little hr will be the number of Hermann cycles. Omega r will be the greatest, and omega r will be the greatest common divisor of all the cycle lengths. And if there's no Fatou cycles, we'll just set omega r to be 1. So what I proved was that if r is a rational function of degree greater than 1, then K1 is going to be isomorphic to the kernel of this matrix. And so by the matrix, I just mean, so it's going to induce a group homomorphism on the free abelian group generated by the critical points and this extra index into the free abelian group generated by the Hermann cycles and extra index here. So By kernel, I mean the kernel of this map. Direct sum Z modulo omega RZ, direct sum the number of 2 cycles minus 1 in absolute value. And then K0 will be the co-kernel of this matrix, direct sum the number of 2 cycles plus the number of Fermat cycles minus 1 in absolute value. And the class of the unit will be corresponding to the class of this basis element U in the co-kernel. So what's interesting to me about this is that, so a priori, the dynamics on the Julia set has nothing to do with the dynamics on the Fatou set. Yet the K-theory of this algebra depends almost only on the orientations of Fatou cycles and the number of Fatou cycles. So back in the 1930s, when the field of holomorphic dynamics was in the beginnings, there was 2 approaches to studying rational dynamics. Fatou liked to study them based on the Fatou set. Julia liked to study them based on the Julia set. And so really we're seeing Fatou's ideology taking over in the C-star algebra. Oh, and I should say that you can detect Fatou cycles for certain rational maps which have locally connected Julia sets. But in general, dynamically, there isn't really any known way of detecting Fatou cycles. So it's interesting that the C-star algebra detects Fatou cycles. That doesn't come up in dynamics. So some corollaries. If we restrict our attention to polynomials, then these calculations simplify greatly because polynomials won't have any Fermat cycles. In the case when there's no critical points inside the Julia set, then K0 is going to have some isotropy, and the isotropy is generated by the class of the unit. And otherwise, K0 is free abelian, and K1 is always going to be free abelian. As a corollary from this, we can completely classify when 2 polynomials will have isomorphic C-star algebras, and it just depends on this input data here: critical points, the Fatou sets, the degree. Another corollary is that for a fixed degree, there's only going to be finitely many isomorphism classes of these algebras, and that the number of classes will grow quadratically as the degree grows. And then also I compute a new dynamical invariant for rational dynamics. So if you let this tuple LR be just keeping track of the Fatou cycles and their cycle length and order entries from largest to smallest, I show that if 2 rational maps are topologically conjugate on their Julia sets, then their tuples are going to be the same. And this wasn't known in holomorphic dynamics before my result. So how do I do this? How many minutes?
3 minutes?
3 minutes, and then there's time for questions, or?
Yes.
Okay. Okay, so if you look at the correspondence and restrict it to the part of the left action that is mapping into the compacts, that turns out to be just the continuous functions on X off the critical set. And if you do this restriction, that correspondence will define a class in KK. And also, if you look at the inclusion here, iota, this will also define a class in KK. And Pimsner tells us we have a 6-term exact sequence of K theory in this way. And because the K theory of our coefficient algebras are relatively simple, free abelian, we get a splitting of K theory. And so it can just be expressed as the kernel and co-kernel of certain mappings associated to this correspondence. So if we want to compute the K-theory, we only need to compute the kernel and co-kernels of these mappings. So my method for doing this is I show that AB correspondences form a category, one of the objects of the category, and I define what a morphism between correspondences are. This sort of generalizes, so correspondence is like a generalized morphism between C-star algebras. So if you restrict to the case where that morphism is actually a star homomorphism, this morphism just turns out to be sort of a commuting square of star homomorphisms. Okay. And then I show that we have an exact sequence of these correspondences in a certain category, and this induces exact sequences involving these kernel and co-kernel groups. So for example, I have this exact sequence. If I wanted to compute the co-kernel of this mapping here, then I would need to compute this, and then the connecting maps here. And so you reduce the problem to understanding the C-star algebras associated to the dynamics on the whole Riemann sphere and the dynamics on the Fatou set. And that turns out to be quite a bit simpler. So I think that's all I have for today. So thank you for your attention.